Hi there. In this video, we're going to talk about rational functions and how to understand their graphs. So let's take a look at a rational function. All right, this is the rational function we're dealing with. Why is it a rational function? Well, it's because it's a ratio of two polynomials. Notice the numerator is a polynomial and the denominator is a polynomial. That makes it a rational function. Now what I want to do is I want to explore the values of this rational function. Before we just look at the graph, I want to get an idea of what's happening. So I'm going to look at different values of x, and we're going to look at the different values of r of x. You can see them here. So I'm going to position x on the x-axis here, and its value is going to be written over here. And the corresponding value of r of x is going to be expressed right here. So we can see right now that when x is 3.63, r of x is 0.47. Right, so if I were to plug in that number for x and compute it, this is what I would get. So let's move x around. You can see the values of r of x change. Not very much. Now let's see what happens when I bring x closer and closer to 2. All right, it's getting closer and closer to some number. When I put it at 2, what happens? I get a question mark. The computer software doesn't know what to do here. So what's going on? What's wrong with this? So this is one of the things we're going to explore. The other thing I want to explore is when we move past 2, we keep going, the values of r of x are decreasing. Now they're getting pretty small pretty fast here, and as I go over here, look what happens. Look at how big they're getting. These values of r of x are getting quite large negative numbers, but quite large negative numbers. As I get closer and closer to -2, look at those values of r of x. They're getting really big now, right? Very, very big. As I get closer and closer to -2, those values get really, really big. Look at how big they're getting now. We're already in the 700s. Super big. Closer I get to -2, the bigger those numbers get. Now what if I hop to the right of -2? Well, those are also very big numbers. They get bigger as I get close to -2, but notice they're positive. To the left of -2, I'm negative. To the right of -2, I'm positive. So as I keep going here, the values start to go down again. So something really interesting is happening at -2. As I approach -2 from the left, the values of r of x become very large positive numbers. As I approach -2 from the right, the values of r of x become very large negative numbers. So what we want to do is investigate what's going on here. How can we tell what's going on by looking at the expression, and what's going on with the graph? All right, so let's take a piece of paper and look at what we can do with the expression of r of x. One of the things that we can do when we have polynomials is we can factor them, right? So I think that's a good idea here. So pause the video now, factor both the polynomial in the numerator and the denominator, see what you get. Okay, so you've figured that out. This is what you should have gotten. Now, one thing you'll note is that when x is equal to 2, this factor is equal to 0. Now, that should be that should stand out to you as something important, right? Because that means the entire denominator is 0. That means we're dividing by 0. What happens when we divide by 0? We get something undefined. So this explains why, when we were looking at the computer here, it was telling us that when x is 2, it doesn't know what value to give it. It's putting a question mark there. The function's actually undefined there because the denominator is 0. We also see that that same thing happens when x is -2. When x is -2, this factor is 0, and so the whole denominator becomes 0, and so the expression is undefined. And that tells us that something funny is happening near -2. Now, we saw kind of a different behavior there. We saw how values are actually getting close to large values. The computer is actually saying -infinity. It's making its best guess. I would not write that as the answer. That's actually incorrect. The computer doesn't know what to do. Okay? So we noted that we have these two problem spots where the denominator is equal to 0. So this is one thing in rational functions that you're going to want to identify. Where is the denominator 0? That's going to be key features of its graph. Okay, but moving on, what we can do now is we can look for factors that are common in the denominator and in the numerator. If a factor is common to both, we can cancel it out, right? So what we get is we get this function over here. Now we have to be very careful about what we just did. Notice that when x was 2, this function, r of x, was not defined. But this function is defined when x is 2. Therefore, these are actually not exactly the same function. They are not equal when x is equal to 2. However, you'll see that they're equal when x is equal to any other number. So these functions are equal only when x is not equal to 2. So we'll specify that over here. But if x is not equal to 2, this is an alternative way of writing down r of x. Now let's see if we can figure out what was going on when x was negative 2. We saw that we were getting very large values for r of x. Why is that? Well, imagine that we plug in a number for x that's near negative 2. We know we can't plug in negative 2 because that makes the denominator 0. But what about a number near negative 2? What about negative 2.00001? Well, if I plug that number in down here and I add 2 to it, I get negative 0.00001. So I get a very small number in the denominator. The numerator is negative 3.00001, right? So it's not that small, but I'm dividing by something that's very small. If I divide a number by something that's very small, I get something very big. That's explaining that what we were seeing there. Notice in this case, you're going to get a big positive number. We have a negative in the numerator, a negative in the denominator gives us a positive answer overall, a very large positive answer. If I take negative 1.999 and plug it in for x, well, when I add 2 to it, I get 0.001. If I plug negative 1.999 up here, I get negative 2.999. That's not close to 0, but the denominator is. And therefore, the expression overall will be very large. The numerator will be negative, the denominator will be positive, and so overall the expression is negative. And that's exactly what we were seeing there. So just to reiterate, when we're near negative 2 on the right, r of x is a very large negative number. When we're near negative 2 on the left, r of x is a very large positive number. Now let's explore what's going on with the graph. All right, so let me zoom out a little bit so that the graph will fit. And let's show a picture of it. Here's what we're getting. This is a graph of r of x. Notice that on the graph, so here's my value of x, here's the corresponding point on the graph. Notice that as I approach x equal 2, I approach this hole in the graph. Why is there a hole there? Well, that's what we observed. We observed that r is not defined there. So it's defined up to that point, but not at that point. As I move my value of x off to the left, I approach this negative 2. And we said that the value of r of x is going to negative infinity. And that's what we see here. You see this point down here, the value of r of x, it's going down, right? That point is going down to negative infinity. And as we approach negative 2 from the left, the value of r of x, the height of this point, is going up, up and up and up and up and up and up to positive infinity. When these things happen, we draw a vertical asymptote here. This dashed line is the vertical asymptote, and it is not part of the graph of r. It is instead describing what the graph is doing. It's saying that nearby, negative 2, the graph is resembling this vertical line. And sure enough, if I go up to the graph here and look at it up here, as I get close to negative 2, you can see the graph almost looks like that vertical line. And the same thing down below. The graph resembles that vertical line very closely. Now you'll also see here a horizontal asymptote. This horizontal asymptote is saying that the graph resembles that horizontal line. Well, if I go far off to the right, you see it does look like that horizontal line. And if I go far off to the left, you see, yes, it does resemble that horizontal line. So these are just guides. They're not part of the graph. The asymptotes are just giving us descriptions of what the graph is doing nearby. So going back to the expression, when I have a polynomial like this, first I note where it's undefined. That means I'm either going to have an asymptote, a vertical asymptote, or a hole in the graph. How do I tell which one it is? Well, if I can cancel the factor and the resulting expression is defined, that means I'm going to have a hole in the graph. That's what happened when x was 2. When x was 2, I have this hole. Now let's think about why. Why is there just a hole in the graph right here? Why isn't something more wild going on? Well, that has to do with this expression that we said our function was equal to nearby, but not at 2. This expression is totally well defined at 2. There's nothing strange going on. The denominator is not close to 0. There's nothing weird happening near 2. So this expression's fine. In fact, we can look at the graph of that expression. If I graph that expression instead of our expression, it looks like this green curve. It's defined all the way up to 2, at 2, and through 2. It's totally fine. Nothing weird going on here. Now, our original function's equal to this function at all values of x except 2. So our function must look exactly like this except at 2 where it's not defined. If that's the case, the only possibility is that it simply has a hole there. Now, if when I cancel all the common factors, I'm still left with a number that makes the denominator 0, in this case x equals -2, then I know that I have a vertical asymptote. And the equation for that vertical asymptote is x equals -2. Now, how do I find this horizontal asymptote? Well, for the horizontal asymptote, what I do is I imagine x is very large. All right? Well, if x is very large, I have a large number minus 1, still a very large number. It's not very different than that number. If I have 1,000,000 minus 1, it's still close to 1,000,000. And if I have 1,000,000 plus 2, it's still close to 1,000,000. So these numbers are negligible when x is large, so I ignore them. And if I look at what's left over, I see I got x over x. That simplifies to 1. So what we're saying is that when x is very large, r of x is close to 1. And that is why we have a horizontal asymptote going through 1 here. The equation of that horizontal asymptote is y equals 1. One final thing we can do here is talk about the x-intercepts. How do we find the x-intercepts? We can see the x-intercept right here at the point 1, 0. How do we find that? By looking at the expression. Well, that's pretty simple. We are just looking for where the expression ends up equaling 0. Right? So what could possibly make a fraction equal to 0? Well, the only way a fraction can be 0 is if its numerator is 0. So all we do is look at where x minus 1, in this case, is equal to 0. And that happens when x is 1. Now the point, the x-intercept as a point, is the point 1, 0. The y-coordinate will always be 0. Now one thing you do want to be careful of is whatever number you find for your x-intercept value, you want to make sure that's not the number that you excluded, all right? If that corresponds to a hole in the graph, then it doesn't count as an x-intercept.